Thanks. We do have one change in the schedule, which is Amir Caspi has swapped places with Scott, so we'll expect to talk from Scott at 10 o'clock. But in the meantime, it's 9 o'clock, and we'll start with Vic Pizzo, who is ready to go, and we'll talk about an improved HAO instrument to advance CME and CIR forecasting. Thanks, Vic.
Yeah, the top, oops, I gotta turn this on. Okay, it's on now? Yeah. All right. Yeah, I'm gonna talk about how a polar perspective mission might advance forecasting, and with science kind of as a sidelight, of course. But anyway, we'll get to that in a minute here. The first thing I want to get to is that in terms of in situ, I'm not sure I see a whole lot of application for out of the ecliptic measurements and forecasting by itself. So I'm going to concentrate on imaging, but there's a lot that can be done with imaging. You can get a direct view of CIR spiral arms, better idea of 3D shapes and morphology and the evolution of CMEs and CIRs that way. And presumably try to use this in conjunction with in the ecliptic view from L5 or from Earth to get the maximum utility out of the project. Now a little bit of history. There was supposed to be two Ulysses, and one of them was supposed to have an HAO Coronagraph on it, and it got largely built, and then they canceled it, and it's a long story, but anyway, it never made it. But that was cast at the time as mainly looking, having a conventional coronagraph looking at spiral arms and whatnot very near the sun was the intention there. There was no HI kind of instrument as far as I know on that. And that was, it was supposed to be in place after Solwyn had died from being shot down, and after SMM just aged out. But it was before Soho, so there was the way in which that was conceived as a high latitude mission was quite different than what we would do today. Now, what we have had in recent times is a nice complement of instruments from stereo. There were several looking right near the sun, and then there were the HI imagers, near one that went out to about roughly half an AU, and the HI2 that went out further. And of course a Core 2 coronagraph, which we use for forecasting a lot. Now, for this kind of mission, I have to realize this would be kind of a trailblazer in the operational sense. We haven't all been dying to have an out of ecliptic mission in the forecast business exactly, and there's other things to be thought of. And also, if it's a single spacecraft, it's only going to be out of the ecliptic part of the time. If you really wanted to do these things operationally, you might need 2 of these at least, maybe 3. On the other hand, lessons learned would enable tuning for what you want on follow-ons. And NOAA interests, and by interests I mean there, of course, money, put your money where your mouth is kind of thing. They'll depend upon the utility. If you try and sell something brand new like this to NOAA, you're probably not going to get a lot of money. You'll get interest, but sympathy, I guess is the word, but not money. What would we like to do with a polar coronagraph? Well, it has, and I'll explain it for a minute why I'm going to concentrate on HIs, but basically what you can do with a coronagraph is some of what they were originally intending to do with the old Ulysses mission. You'd look at, and it's been discussed somewhat here, which is you'd look at the roots of the CIRs, you'd look at regular, normal, and pseudo streamers. You could get a different view of the slow flow in the ecliptic plane. There's a lot of things you could do. The main thing from our standpoint is you'd get a top view of the CMEs, which gives you a little more of a 3D idea of what's going on there. But the question is, how well can you do this and see this? And I want to really emphasize, with 2 views, you're not doing tomography. It's really very different, and I think you need to kind of gauge what you're going to get out of it quite differently. So let me see. I hope this was going to work. Let's see if it will start. Right, yeah, okay. This is a highly processed, from the slurry pipeline, imagery from HI1. And this is showing the outflow from the corona over a month's time. This is near solar max. What you see is there's a hell of a lot going on, and there's a lot of stuff on top of each other there. And occasionally, like towards the end of this, there will be a big CME that you can kind of see. It's real spectacular. It's the one I'll be talking about actually later. But this is kind of what you're going to have to work with. You're not looking at solid objects sitting there that you can differentiate. It's things laid on top of each other. And Craig likes to use the word caustics, and it simply means you have optically thin situation, things are on top of each other, and your ability to differentiate what's on top of what and what goes with what is not guaranteed. So why I think the emphasis should be on HI1 field of view? Well, it's a lot of dynamics going on here. And basically, if you can get the speed, direction, and timing of a CME at half an AU, by then, it has gone through a lot of deceleration. I'll explain why in a minute. But basically, they're just kind of coasting along pretty much after that. And if you know what's going on at half an AU in terms of where the CME is, what its direction is, you can come up with a really accurate forecast. And a combination of polar and equatorial views should be able to do a good estimate with, and good enough for government work, as they say. Now, there are three sources of mass in any CME that's being ejected. One is it's the blob thing, the flux rope, the object we all call a CME without actually defining it so well. I mean, there was a session at the last Solar Wind, or not Solar Wind, but Shine conference where we spent about an hour just getting everybody to agree what a CME was. But everybody knows what it is by sight, but definitions differ. But anyway, I'm talking about the flux rope part, the main ejecta. There's mass that comes out with that. There's also mass that comes out after the ejecta, behind it, because the corona opens up briefly, maybe a day or two, but there's fast thin flow behind that, and mass is coming out. It's more mass than what would normally be there. And then finally, there's the mass that's piling up in the front of this thing, and that's what I'm going to concentrate on, because for the forecasting role, and actually for some of the science, that really needs to be understood real well what's happening there. But most of when people look at coronagraphs and trying to deduce how much mass came out with the thing, it's largely swept up mass is the bigger part. You can kind of see this. This is another paper by the Swery group here, where they looked at a particular event in 2008. And what they did was they did mass estimates in the Core 2 field of view, in the HI1 field of view, and the HI2 field of view. And you kind of see that the accretion of mass at the front end of these things, as it goes out through the system, it's sweeping up, because the CME is coming out faster than the background solar wind, it's sweeping up all this material in front of it, and it's pretty substantial. Depends upon the speed with which you come out, the breadth of the front, and all this kind of thing. But it's not a minor effect. It's really a big effect. And in particular, what hits Earth, what we think is the CME, with all this mass, that's what we're counting. Now I'm going to concentrate here on just one CME because I think it contains it demonstrates a lot of the issues that we run into in the forecasting business, and actually in the science business. People really don't, how do I say this? After all these years, people really don't, including me, know exactly how to interpret some of these views in a really multidimensional sense. People fool themselves a lot. They think they know a lot more than they do. There's a lot of unknowns here, and I'm going to try and illustrate some of them with this particular example. There was a CME at this time period in 2011 that went off at kind of about a 30 degree to the sun-Earth line. And stereo was in the positions that you see there, the red and blue, and then Earth there. And what was seen from stereo was this view here. And the side on stereo A, which is on the right there, it was pretty much a side view, it was a really nice limb view. And from B is you're kind of looking from the butt end of this thing, kind of looking, not the best view, but you got a good view of it. And in both cases here, you can see a very complicated, this is one of these nice big ones that has all this halo kind of activity with it. But you can see the core ejecta here really well in stereo A. Stereo B, you can see it here, but what you also see in B is you can kind of see this thing here, which in my view, that is what I'm calling, what we would call in SWIPSI, the ejecta is this part here. But you can see the whole corona is getting perturbed. There's this kind of big wave kind of phenomenon going out in front of it, and you can kind of see it pretty well over here. Now, the NASA Forecasting Center used just stereo, these two views, and got a very good forecast, largely because this thing is right on the limb, and they kind of knew where the source region was. Now, at SWIPSI, we just kind of turned on, not too long before that, and it's one of the first CMEs we looked at, and we used Soho imagery and got this really wrong, and I'm going to try and explain why, because it's a kind of important thing to kind of figure out what's wrong, what's not. All right, here's HI, which we did not use it, or have not yet used at SWIPSI for forecasting. Other people have used it in various experimental ways, but and this is from that pipeline, where this is highly processed imagery now. The star field's taken out, a lot of defects and whatnot, and it really gives you a very good view of what's happened in this event. Now, in this event, this structure was sitting there prior to the event, and then here is where the ejecta starts, but you can kind of see this whole big disturbance out, which is much bigger than this part. And what you see progressing in time, going this way, is this stuff just sits here, because that's kind of back to front. Just wavy, this whole big front kind of expands. You can kind of see a structure here. You can kind of see the structure there even more. And then on the next view, I think it's one of the, I hope the contrast is good enough in here with the lights and everything. But you can see there's really a structure sitting here, and that thing is about 30 degrees out of the up from the equator, as it turns out. But you see this stuff out here still, and notice that this is going out faster at this point than this is. All right, so this is kind of a side disturbance going on, and what you can see here, I'll get to kind of more interpretation of it in just a minute, but here is another plot, kind of a nice ideal shade surface plot thing, showing the CME at two different times. This one is just before the start. This one is pretty late, near that last image I showed you. And you can kind of see that stuff I was pointing out is right there, okay? And you can kind of tell there's things out here. But the signal to noise here isn't exactly wonderful. I mean, it leaves a lot to be desired. So your ability to see these things, even with this really highly processed imagery, is not good. For forecasting purposes, you'd like to see a lot more of what's going on here. And using HI2, in fact, doesn't help you a lot, because the signal to noise is just not very good. You can tell this thing is kind of here, and you can tell something is happening here. Now, one of the things I want to actually go back here, back to this slide, and talking about this mass, where it comes from. Well, what's happening is, again, as the CME goes out from the sun, it is picking up the mass in front of it, because you're in a hypersonic regime. Basically, the flow, the steady flow, if it is steady, or whatever flows in front of the CME, is trapped there. It can't go sideways very fast, because the geometry is diverging, the characteristic speeds are very small. It can't move sideways. It's just stuck there. And so that's where a lot of this mass is coming from, and most of that mass, if you do some numbers and look at some typical values of the solar wind speed in the CME, most of this happens by about half an AU, which is the outer part of that field of view I just showed you. That's why we're really interested in that. Because we want to know where that is. Now, let me show you, now I want to explain here, we saw from that the actual ejecta was about 30 degrees north-south, or to the north, was the direction. We looked at the stereo imagery in fitting this, but we also looked at Soho. This was the view from Soho. Now, trying to reconcile that with the other two views is no easy thing. And in doing this, we decided to go more with the Soho view than with the, with the stereo view. And it's really mixed up, and you see this a lot in these really energetic events, that it's very hard from the different views to kind of reconcile all of what you're seeing. And part of it, I think, is I'm calling this a head fake from the corona, because it's like in sports, you know, if you want to, you know, dribble to the right or something, you kind of look to your left and throw the guy off and try and go around him that way. This is actually one of these things in coronal physics that people has been sitting there for a long time, this effect. But basically what's happening here, remember I said this is coming out at 30 degrees of the sun-Earth line. That means the outer edge of that main ejecta is over near the plane of sky. And as that comes out through the corona, it's pushing things sideways, and it's pushing material that formerly was more nearly, like say 45 degrees from the Earth sunline. It's pushing it up towards the plane of sky. So it's becoming visible. So from Soho, I mean, this was completely confusing, and we bought this, by the way. So consequently, our forecast was way the heck off, because this is largely material that's not really part of the CME. It's just real bright. And this is one of the things about, like, again, like I'm saying, about when people look at coronagraphs, they do all kinds of, make all kinds of assumptions they don't realize they're making. And this is something I think needs to be worked on a lot more. Maybe we're at a juncture where we can actually revisit a lot of this stuff. We recently had, for example, a funding opportunity, and I was kind of hoping somebody would put in a proposal saying, we'll look at this whole imaging business and what you can see in the coronagraphs and how you can better interpret what you're seeing, and really get it kind of organized and well worked out. And nobody did that. They proposed some good things, some kind of really off-the-wall things, but that was one of the things that was not proposed at all, and there also was nothing proposed to do with like HI field of view, which I thought was kind of strange. Maybe, but this was a one-year proposal, so maybe that had a lot to do with it. I don't know. But hoping in another round that we have that people will come back and revisit some of this stuff, because there's lessons here. So also, again, going back to the Polar Perspectives mission, what we'd like to have is an HI. I would like to forget about HI2 field of view, frankly. Put the money into HI1, get the signal to noise in that area really up, really pump that up, and get a much better instrument there. Because this is the best way to kind of isolate the different parts of the CME that you're seeing. Now, some of it is the ejecta blob, some of it is just the corona, so it's like a blast wave phenomena going off around the side. And for forecasting and science, you want to know the difference. And then finally, you're probably going to, if you have adequate signal to noise for polarization, that could be really, really useful in kind of distinguishing what's where in this business. So finally, as I was trying to say, the coronal signal is very complicated. It's not, I don't think it's appreciated widely about how complicated it is. People make all kinds of weird ideas about things. But if you can crack this, you can get improved estimates of the direction and speed. You could probably get the east-west ambiguity, or the east-west is the least well-measured thing in the current, when you're viewing from the ecliptic. And you can get that angle better with a polar view. And again, I'll just say I think polarization will be pretty important for this. So.
Thank you. All right, we have time for a few questions. Chip? Could you use the microphone there? I'm sorry. Thanks.
Very nice talk. You make some really good points with that. I was wondering if one of the things that could be added to this would be charge state composition, so we could really pick out some of those features that you're talking about. If we could get in situ observations, maybe combine that. I mean, most of these aren't going to be polar directed, But if the spacecraft are in orbit, some sort of a polar orbit, and they do pass through the CME, if you could get charge state composition to make comparisons with the ejecta, the filament material, compressed material, and the shock, it would really add another whole dimension to identifying the material.
Yeah, and that's a science question. That's why that's why I initially said, from the forecast standpoint, you don't care about that.
Yeah, that's true.
But for the science part, you really do.
Absolutely.
And you're right. If this is mainly a science mission, you want to do that.
Yeah, absolutely. So I appreciate the point you're making, and yeah, this is definitely sort of a complementary point of view that could be beneficial.
Please, Michael.
I was wondering if you could just elaborate a little bit on the signal-to-noise improvements. Getting outside of the ecliptic, you reduced a lot of the zodiacal light that I know is a big issue in prepping the images for core images. And could you describe a little bit more what other requirements you have for increasing that signal-to-noise?
As far as the sources and all that, I mean, I'm not a hardware, HI builder kind of guy like would be here. But basically, we just need to get signal to noise up enough that ghost-like thing I was showing you there is enough to kind of get a sense of direction. But you don't get much else out of that. And if you're really going to do this, and that was a pretty bright one. I mean, there's a lot of cases that aren't this bright and this well-defined. And so what you want is enough signal to noise that you can see any structure like this that is occurring in that HI field of view. And right now, it's kind of right at the limits. I mean, this is, like I say, one of the better examples I could find in that highly processed SORI line.
I'm going to throw in one of my own, which is, of course, you're singing my tune here on mass accretion and the complexity of the CMEs. You mentioned polarization at the end. Would polarization help you from the polar vantage, or is the ecliptic view enough?
Well, if we could get it from in the ecliptic view, it would certainly be highly useful. I think, but the problem is, again, you're trying to sort out things that are laying on top of each other. And from any one view, it's really pretty hard. I think that's why you need to, even with polarization, that gives you a better idea of where things are. But in white light, like we have here, it's like you're completely at a loss. And so definitely you'd want to know now. For forecasting, the question would become, will polarization help you localize this, the core of this thing, what I'm calling the ejecta? That's what you really want to know. And it's kind of unknown. I mean, it's a lot about this idea. I mean, if we go to high latitudes, you just see what you can do. You're still going to have the same overlap problems, but maybe not quite the same. And it might vary depending upon the solar cycle. When the current sheet's really very flat, maybe some of that goes away. I mean, you have a pretty good idea if things come out of the ecliptic, you're going to see them pretty well. So, on the other hand, if you do that during solar max, it's going to be pretty confused or overlapping. Yeah.
One more question from Nariaki, and Carl can come up and start preparing.
Showed a very complicated example of 2011, yes, and is it true that there'll be no help from images closer to the sun to understand the origin? Because even if we have information at 0.85 AU, maybe it may not be enough to predict when it comes what the impact will be.
Yeah, well, you don't get everything, but you just get a better idea of where things are and whether they're pointed right at you or not pointed right at you, like in that example. But you're right, and it's a lot. You only get so much out of this.
All right, let's thank Vic again. And next up, we'll have Carl Henne talking about forecasting space weather with global magnetic patterns.